Some of the things that we're doing differently this year is to add items that you normally wouldn't really consider HPC. But HPC definitely has a big influence on them, and that's cloud and big data. Cloud, we're having start today with our keynote speaker from Ivana from the University of Vienna. And we're very, very happy for her to be here, to provide some insight in terms of some of the challenges that are happening within the cloud. And tomorrow we're going to be talking about big data, which Dr. Panda will go in some details there. So just a few different parts of HPC that we haven't normally talked about, but you're beginning to hear about. That's essentially within this realm, and I think all of us can really have an influence over it. So with that, I'd like to bring up Ivana.
Good morning, everyone. So welcome to my talk, and thank you very much for the introduction. Also, thank you very much for the invitation to Brian and Gillard to give this talk. I just have had a glance to the agenda of yesterday. So I saw that there were a lot of technical talks about clusters, about technological challenges in building clusters, and so on. So I think today it's quite a different talk I'm starting the day with. I will talk about the challenges in establishment of cloud markets. That means how can we place products, HPC products, which are shaped as a cloud products on a market. What are the challenges here? How can we define products, and how can we define the markets? And there are a lot of challenges, there are a lot of open issues that have to be solved before we can define open cloud markets. And before I start my talk, I would like to emphasize that the work that I'm presenting today is supported by the Vienna Science and Technology Fund, and also by the Self-Awareness Initiative of Autonomic Systems. It is a European initiative. Okay. So the first challenge before we start talking about cloud markets, I would like to explain is definition. What is a good, what is a standardization process, and what is a market? So on this picture you can see the clear difference between the real goods and between the virtual goods. So on the one hand, we have these traditional goods like, I don't know, a bottle of water, of a camera, or a car, or bread, or something that we know what is it, we know how to buy it, we know about the quality, expected quality we want to have when we buy such goods. We know where we can buy it. I know I can go to the supermarket and buy a bottle of water. Or I know I go to my car dealer and I can start negotiation on a car price. So I usually also know the process, how I can achieve a good price when I'm buying real goods. Well, if we think about HPC, if we think about the clouds where we have software, where we have data, where we have computational infrastructures, so it's not that easy to determine what is the process of defining a price. What is the cloud product? How should, for example, a data cloud storage offer should look like? What are the attributes I have to provide to my consumer to decide whether they want to buy my product or not? And the next challenge is, okay, once I have defined the good, the virtualized good, so how should the market look like? Where can I place my products? Where can I achieve highly liquid markets where I have the chance to sell something and also to buy something? So if you look at this picture here, so you can see a clear challenge in electronic markets. So you can see here a very characteristic a typical characteristic of electronic markets that is used to assess the quality of the market, and that is liquidity. Liquidity means the chance to buy or to sell something. So if I go to the supermarket and want to buy water, so the chance is quite high that I will find water in that market. Yeah. If I want to buy specific cloud product and I enter a market, so I have no idea about the chance whether I will find what I need. And here you can see a simulation where we simulated different resource types that are offered at the market. We simulated with 5,000 resource types, and we've simulated with 10,000 resource types. And also up to more than 276 resource types. So you can see that the chances to get your product sold on the market decreases dramatically if we increase the number of resources. So what is the result of this observation, of this simulation? We have to define a specific number of resource type. So we cannot offer a cloud market with 10,000 resource types or 5,000 resource types, or even 100 is maybe too much. So we have to limit the number of types of goods that we offer on a market in order to increase the chance to have a liquid market. Otherwise, if the market is not liquid, there is no chance to buy or sell something. Okay, so let's see today's cloud landscape. So what do we have? So we have a number of providers. We have Google App Engine, we have Amazon services, we have SAP, we have different providers which provide software as a service, platform as a service, infrastructure as a service. So the question is now, how can we get what we need? Do we have directly to negotiate with the provider? Do we have to go to a market where we have different offers from different providers where we can select the best one for us? And the challenges are, of course, here large variety of services that we have here, considering software, platform, or infrastructure as a service, then dynamic participation, which results in low market liquidity and low sustainability of the market. And that are the challenges that we address in our group at Vienna University of Technology, where we try to define solutions in order to define cloud markets with high liquidity and also with a certain number of products that make possible to achieve a certain liquidity of the market. So how can we solve these issues? How can we define products and how can we define markets? Well, we use a very, very simple approach. So we look here at the human body. So it's a very, I would say, perfect system that we have here that can optimize themselves considering different environmental conditions. So just imagine increase of the temperature in this room. So what do? We don't think about that. Our body suddenly increases transpiration. So that's something that happens autonomically. So the idea here is to define markets which are able to act autonomically, to analyze different influences of the environmental changes, to analyze different changes of the infrastructure the market is running on, to assess different market goals and changes on the user or provider base, and then to optimize the market autonomically. And that's also not that easy because there is a danger to over-manage the market. That means there should be a kind of balance between management and self-intrusiveness. So that is also one of the challenges that we are trying to solve. So now I will talk today about two different challenges here. So the first challenge is how can we define the products? So if we have, imagine we have a market and we want to define products. So the question is here, how many do we need in order to have a certain liquidity on the market? Do we need 1, 5, 10, 100? How can we assess the number that we need? That's the first question. The second question is, how should the product look like? Which attributes do we need to define the product? Which attributes do we need to put into service level agreements to achieve a trade, to achieve a market where we have a certain chance to sell that product? That's the first question. The second question is, how should the market look like? So imagine here certain characteristics of the market, like market participation rules, size of the market, and so on. That's something that we can measure, that's something that we can assess. And then there are certain goals of the market, like we want to achieve certain liquidity or connectivity. Imagine all those social network platforms that we have at the moment. Maybe we can profit from the connectivity from different platforms where we have on-demand combine markets or distribute markets, change the size of the market, and so on. And then there are some parameters like number of users that is not constant, that changes over time. So we have to monitor it all the time. And also the number of products and the characteristics of the products. It is nothing that is static on the market. So that is something that we have to monitor, to change, to adapt. So these are the two challenges that I'm talking today. So here you can see, I would say, the evolution of research on this slide. So we started with this idea of autonomic computing, where we try to mimic biological systems. And then the first challenge was to use something biological and to define something technological. So here you can see our first outcome, how the autonomic system could look like. So we have here clear components. We need sensors. We have to sense the environmental changes in some way. Then we need this, it's called MAPE cycle, where we have monitoring, analysis, planning, and then the execution. We have to monitor what is changing. We have to plan what are the possible changes to the market structure. We have to analyze it and then to execute. And finally, we need actuators. We need software actuators to make changes of the market, to make changes of the product. And then you can see the next step in the research evolution is the impact of what we have developed. So the first results of our market, self-aware market, and also dynamic product definition is that we developed energy-efficient clouds, where we, on demand, try to outsource or insource computations in order to optimize energy consumption of the certain cloud. I mean, that's not a trivial task. We need mechanisms like federations and so on, but that's the first results that we have achieved. Then another result is, I don't have it in this slide, but we also applied our mechanisms for traffic light management in Austria. So we optimize the management and infrastructure for the coordination of the traffic light in Austria, also based on the observation of the products that we have and on the structure of the service level agreements. And the third impact is we use it for high-performance computing, for bioinformatics, where bioinformatics from the life science faculty use our tools in order to optimize their processes. So let's look into the technical details, how the products can be defined. So first, you can see here how we define the virtual products. So we imagine a market directory where we have public service level agreements. So I don't know whether you know what is a service level agreement, but it's a kind of a term, it's a kind of an artifact where we can state the characteristics of the goods and how the goods are sold and how we can buy that. We put a kind of attributes, for example, what we want to buy and certain values for those attributes. So in a market directory, we can put public service level agreements. So we assume that every user organization has a private template, something that cannot be changed. That means sometimes we have service level agreements that are used in business processes and cannot be changed anymore. So I cannot change my private template whenever I'm using another product. That means I have to bridge the difference between those templates. And in our cases, we define mappings. Yeah, that is something that tries to bridge the difference between two templates. If I have a template which is in a public directory and I have my private template, so I can somehow translate between those. Then in the next step, I define the mapping, and if it's necessary, I can also say, well, I would like to have a certain attribute in your template. For example, you don't offer attribute number of course, and that is something crucial in order to assess whether I can use your offer or not. So I can express my wishes that can be then included into the template maybe in the future, in the next time step. Yeah. The same can happen for service consumer. So we have service provider and service consumer. They can do the same. Okay, they can say, okay, I have my private template. There is something in between. So I have to translate. So the mappings you can imagine, like I try to speak someone who speaks Spanish, yeah, and I speak only German. So what should I do in that case? We try to map. I map to English, yeah, and then he maps from English to Spanish. So that's a kind of mapping, service level agreement mapping. So. Yeah, I'm lucky if I find someone who speaks both languages, so we can translate. That is the same here. The idea is the same. We try to translate to something that everyone understands, and then we try to translate back that is defined in the private template, in my private process, in my mind. Yeah. So the next step here is that we have now to check, okay, what is happening to the public template? Yeah, we don't have to, we don't want to have a static public template. We want to reflect the needs of the consumer base. So from time to time, we have to analyze all those mappings. Yeah, and that's a very tricky part. That's research. We have to analyze all the mappings. We have to analyze what is happening in our templates, and then we have to decide: do we have to change it? And that also considered costs, because sometimes we will change template that do not reflect the base of the whole consumer base, just a few of them. So we have to balance what is the impact, what are the costs, and that's a research direction on its own. Just to decide how to change the SLA templates. So. Yeah, and then once we have a public template in the next stage, we can then assign the templates to the users and to the providers. So that's the conclusion of this approach. How can we define the public templates? Okay, so maybe some of you are just wondering, how do you do it technically? So the mappings are very, very simple. So we use style sheets. In the simplest case, it can be a style sheet where I translate between two attributes. So that is the very, very simple case. Of course, we can have more complex cases where we have future wishes, where we add some wishes that we want to have in our public templates. But here you can see a typical example where we translate between local templates and remote templates. So you have to write the rule for the translation from local to remote, then you have style sheet transformations, and then you achieve your final template. So the technology behind it is a very, very simple. So, how does the management of the definition of templates looks like? So, you can see here an example we use for the definition of medical templates, used for the medical processes. So, usually we have a medical app template that is used for all processes that we have, for example, in a hospital. So then, we try to group it by structure. That means we try to group the templates based on the application area. So sometimes there are templates used for the cardiology, templates for surgery, and also for oncology. And they have different attributes necessary to define service level agreements. So in the next step, we try to group by service level objective values. That means we look into the content of the service level agreements. And then we can see that some templates are data intensive, surgical apps, and they need specific service level attributes, and other are simple surgical apps. So what happens here? What do we identify here in this process? If we compare it to real goods, so here we try to identify which types of product do we have here. For example, here's my bread and here's my water, yeah, to simplify it, yeah. And then in the next step, we have to identify how to shape the bottle of water. Yeah, what is the shape of the bottle of water? Do we need 1 liter, half liter, or even more than 1 liter? So in essence, this is what happens here. For the real goods, it's already defined, it's proved, we know it, and the people are also fine to use it. So if I go to the supermarket, I don't expect to buy 3 liter of water. I know that I have certain ranges that I can buy. And for virtual products, for cloud products, we don't have these expectations. We don't, because the expectations are so different. And that's the reason why we have to analyze the needs of the users, and the only way to do that is to analyze service level agreements that they provide to us. And that's what happens here. Okay, and now the question, how can we do it automatically? So doing manually, it's nice, but time consuming, doesn't work well in all cases. So we use clustering algorithms in order to identify the groups of products. So the clustering algorithms are very nice approach to find structures in collection on unlabeled data. Yeah, and here we have a goal to determine the intrinsic group of set of unlabeled data. And for that reason, we use 2 algorithms. We use dbSCAM and k-means. And here on this picture, you can see the result of the application of the clustering algorithms. So at the beginning, you have these sets of data without any connection. I mean, here is very simplified. You can see with your eyes, okay, we have 4 clusters, and they belong to these 4 groups. But in practice, it's more complicated, so it's not so obvious. And after the result of the clustering algorithms, we have clearly identified cluster. Here we can, for example, say, here is my medical application for surgical apps, here is my application for oncological apps, and there is my application for cardiology apps. And here again, we can map it to the real products. So the number of clusters identifies the products, and then the content of the cluster identifies the attributes of the product. Again, half liter of water, 1 liter of water. What do we need here? Okay. Sure, we cannot define anything without math. Here are some, just to give you an idea how easily we can quantify our decisions. So for example, if we want to decide how good the templates match between the public and private, so we just give numbers. For example, if we have a property P, like number of cores in template 1, and we have it in template 2, so the distance between the templates is 0. Okay, so if we have it in template 1 and not in template 2, so the distance the distance is 1. If the property differs in only one property differs in one template or another, then we also assign 1. And if both properties, for example, differ in both templates, so we assign the distance of 2. And that's something that we can start thinking. We can generate accumulated sum. We can analyze it over time, and so on and so on. This is just to give you an idea how we can calculate the distance between parameters in a template. And here you can see how we calculate the values. That means half a liter of water or 1 liter of water. What do we need? So we use here Hausdorff distance. So you can see clear, if here we have 2 values, so we try to find the maximum distance between 2 values in a set of an attributes. And that's the way how we quantify the differences between 2 attributes and also the values of an attribute. Okay, here is just a presentation of 3 methods. How can we then evaluate the clusters and decide whether a new attribute in a template should be taken or deleted? So we have 3 different methods. We have a maximum method where simply you can see the maximum attribute over iteration in time is selected. Then we have threshold method where we say, okay, if certain threshold is achieved, then we select this attribute, or we say a significant change method that we say if this change between two iterations in a time is, for example, 15%, then we select a specific attribute. And here is also to show you how we deal with the changes if, for example, we change an attribute that does not reflect a specific user requirement. So we have also to take care of changing templates and leaving user with new version of a template that does not reflect their needs. So in that reason, we define artificial mappings. Yeah. So if we, for example, in the next time step, change the public template and the user is not aware of it, so we have to keep track of it. And then you can see here, if we define the mappings between the user template and the initial template, and also between the initial and the new template, we can automatically, in a transitive way, define the mappings between the user and between the new template. So we are also aware of that if the definition of goods is getting worse for some group of users, we can manage that, of course. Okay. Yeah, here is just an example how we calculate the cost and utility of definition of products. So we calculate the overall net utility as the difference between the overall utility and overall costs. And here are just the examples how we quantify the costs and the utility. For example, the utility is 0 if the parameter does not exist in my template, and the utility is 3 if the templates do not differ with respect to the parameter. That means everything matches. Yeah, and here is the same for the cost. So we can also assign some numbers. For example, there are no costs if the users don't need new mapping, and the 5 is if the users have to change the template because the public template is changed. So that's the worst option that can happen. And that's the way how we quantify the decisions. So now I would just like to give you an idea how self-aware market works. Okay, what is a self-aware market? A self-aware market has a knowledge of the market and knows how to react in specific situation. So the key ideas here are self-configuration, self-healing, self-optimization, and also self-protection. And we say also that market is self-aware and autonomic if once established can optimize themselves and react without human interaction. And that's also what we want to achieve here. So here is an example how we define a self-aware market. So first we start with the market implementation. So what do we know? What do we need here? We need market infrastructure, that are the facilities that the market runs on. We need middleware for the operation of the market, and we need a market allocation mechanisms. That is usually a kind of auction, for example, continuous double auction or English reverse auction or something like that. And then we need a service directory where we can access service level agreements. And that is usually connected with the application of the users, as you can see here. So what is then happening? We try to sense the market. We try to sense what do we measure on the market? What are the market characteristics? So for that reason, we, as already mentioned, apply typical MAPE loop, autonomic MAPE loop, where we have monitoring, then where we have analysis, planning, and execution, as you can see here. So based on the monitoring and the knowledge that we have here, we can then react. We can then change market properties. And that is not trivial, and that is something where we try to define a generic way to monitor a market. Because what you monitor on the low level is not what you have to guarantee on the market level. And so here are just examples from the monitoring methodologies and the gap, what we measure at one hand and what we have to the guarantee at the market level. So here you can see the metrics that you can usually directly measure at a market, no matter whether you use English reverse auction, continuous double auction, Dutch auction or whatever. So usually you can measure immediacy of matching, average price bids, average price requests, number of allocated resources, price matching, participation costs on market platform, computational time to calculate a price, to define an offer, or costs for platform resources. That's something that you can easily and directly measure at the low level of your infrastructure and market allocation mechanism. So something that we want to guarantee, something that we want to analyze are market goals. I already mentioned liquidity is very crucial. If we don't have a high liquidity on a market or above a certain threshold, so we have no chance to buy or sell something. So how can we measure liquidity? So that is we can directly compute it using immediacy of matching. So the next goal of the market is a low bid-ask spread. So we don't want such prices that are requested or offered and such prices that are offered. So there should be a kind of matching between what is offered and what is requested. So that is something that can be calculated using average price bid and average price requests. The next parameter is market depth. That can be directly calculated using number of allocated resources. And then the next is provider revenue. So that is also something that should be at a certain level if we want to operate a market. So we can calculate it using number of allocated resources and the price of matching. And so on and so on. We have, for example, execution costs that is calculated using computational time, number of platform resources, cost for platform resources, and so on. So you can see here are the metrics that we can measure, and here is something that we have to calculate, analyze in order to define liquid markets. And here is where we start to analyze, okay, what are the parameters? What are the critical thresholds? What are the critical thresholds to generate a market, to operate a market? And for that reason, we performed a lot of simulations to learn about the typical market constitutions and typical market characteristics that we can have. For that reason, we used GridSim. It's a kind of market simulation package that uses JavaSim simulation kernel, where I can use all these messaging mechanisms in order to simulate the market. Then we have a data computational grid where we can manage resources like job management, reservation data, resource allocation mechanisms. And then we have different user code. We have a layer with a user code where we can plug in different mechanisms we want to evaluate. So we can plug in different user scenarios. We can plug in different scenarios that we want to evaluate. For example, what is the behavior if you use some typical scheduling mechanism in order to perform a performance study or different other evaluation scenarios. So what we had to develop here is exactly this mapping that I have explained. So we have the infrastructure sensors, we have market sensors and mechanism sensors. So we have to calculate and to translate between the infrastructure sensors that we can measure and between mechanism sensors that have to be calculated on demand. So if you look back at this picture, what happens on the right-hand side of the next slide is exactly this mapping here. And here are just some simulations to show you the outcome of the evaluation of the monitoring mechanisms that we have implemented. So here you can see a typical situation on the market, on the electronic market, where we use continuous double auction. So everything is fine on the certain point of time when the providers start to submit their offers, because they already submitted everything. So in that case, the total number of asks increases dramatically because the users don't get a match. Yeah. What is the result of this situation on the market? So suddenly, the prices used as the market, they drops down. So usually we would expect that if the demand is increasing, so the prices would also increase. But our simulation shown that because we have a number of low price asks, and that's the nature of the continuous double auction, so the probability to sell for a low price is higher. And that's the reason we got a lot of matches for low prices. So that's very, I would say, unusual situation in an electronic market that happens. And it's very different to the traditional markets. So you can easily see here the prices that are achieved, they drops down almost to the half of the initial prices that we have. So that's one very, very useful observation on an electronic market. And if you look, try to evaluate the simulation results, so you can see here what happens. Here is something that we directly measure at the market level, and here are our goals. So using the mappings that I have already explained, we can easily map between what is happening here and the values here. So we can easily see what is being and what is getting worse on the market. So we can see here that the market depth is not okay, immediacy, platform revenue, number of allocations, execution of costs, and so on and so on. So that's the first step. That's the first step in establishment of self-aware markets. The first step is to define a methodology where we can monitor the market. And here is clear how we can manage and monitor the goals of the market. So that's the first step. Once we can monitor the market, then we can plan, analyze, execute, and so on and so on and so on and so on. Okay, so I'm running out of time. To give you an idea how we use it. So here you can see a typical bioinformatic applications used by our colleagues from life science faculty in Vienna. So they use protein alignment in order to discover new structures in protein, and that's it's data and intensive. They use a number of resources, and usually they perform manual tasks to assign data, to perform alignment, to use tools that are running locally or remotely, and they use, I don't know, scripts to assess the data, to analyze the data, to upload the data, to download the data, and usually they waste a lot of time doing that. So they are managing their workflows and processes manually. So we applied our mechanisms, and you can see here their workflow. We just plugged monitoring agents to each manual task they have here, and we assigned our monitoring and autonomic management middleware, where we can on demand assess the values and monitor the values of the local tasks, of the data management tasks. So we can in advance reallocate resources. So if we for example see, okay, they're running out of memory, so we can on time just use Cloud Federation's mechanism and outsource the computational tasks. So that's one application of the market mechanisms that we use here. The next application is optimization of energy consumption in clouds. So you can see here a visualization done by one of my PhD students. Here you can see distribution of load on different physical machines. On each physical machine we have 2 virtual machines. So using the monitoring and analysis phase of our autonomic computing, we can, in just 4 time steps, I mean that's a very simple setting. we usually don't have just 8 PMs, we have 800 of PMs or so. But this is just to visualize the results. We can automatically assign, okay, if we put all the load on 2 virtual machines, then we can switch off physical machines that are without load anymore, and then we can power on and save energy. You can see here the green are, they don't consume any energy, and that increases the energy efficiency of the whole cluster, of the whole data center or whatever. So that's just to show you how we applied, and this is also joint work with Jean-Marc Piasson and Georges Dacosta from University Paul Sabatier from Toulouse, France. Okay. What do we have to do in the future? We have, of course, to define the whole phases. We have to define analysis, planning phase, execution phase. We are now at the monitoring phase. But even though with just the monitoring phase, we achieved quite a nice results in application to bioinformatic workflows and also to greening ICT. So in the next step, we will try to apply it to different data applications. So I would like to thank all my colleagues. The work that I have presented today is joint work with many collaborators. So most of the work was done by Ivan Brešković, who performed all the simulations and also definition of the market. Then Vincent Macaroja, Michael Maura. We are from Vienna University of Technology. And then we defined the first prototype for the market monitor in collaboration with Karlsruhe Institute of Technology. So they are experts on network economics, and we work with Christian Haas and Simon Caton. And we also work with Jörn Altmann from Seoul National University, who also developed the foundational elements for the definition of computational economics in networks. So thank you very much for your attention. If there are any questions, please feel free to ask.